Hey, good morning, everybody. This is some more discussion on the ideas that are showing up here in chapter 7 and 8. They're really kind of tied at the hip, and you really kind of can't do one without the other. So chapter 7 is containing a lot of preliminary material, the idea of work. That is, you push something, you put a net force on something, and it actually moves. And when it does that, then you have changed its kinetic energy. You have changed its velocity, or you might push it and you may give it a new position. Or you could push it and that energy that you put in could get wasted on something like friction or something like that. And so we'll be taking a look at all those types of situations here today. Okay, so let's move on to chapter 8. And really the big idea in chapter 8 is all of this talk about dot products and work and energy stored in a spring and so forth is really important, because the fundamental law that our universe is playing by, that we have found so far to be true, is that this idea of energy is conserved. And if you can say that there is some sort of quantity that nature is keeping track of in all interactions, that's a very deep understanding of what's really taking place. Now, I don't think we understand why nature does this, but as long as it keeps doing this, it gives you great predictive power of exactly what's going to be taking place in all sorts of systems and so forth. So in chapter 8, we start off with this idea of conservative and non-conservative forces. And there will be for those that go on in physics and so forth, there'll be a very, very delicate test here of what's a conservative force and what's a non-conservative force, and it'll be a mathematical test using the gradient of a vector field. Now, a lot of you have not seen that type of mathematics so far, so we'll look at this at a much different, little more conceptual level. But forces will kind of come into to us in these two packages, and it really means something to us eventually mathematically on how we treat that force when it comes to how it's doing work on an object, and how maybe those energies are conserved or not conserved. So a conservative force right now for us would be a force that we're going to say is path independent. Okay. And so that might seem sort of odd here, but I'll try to get this to make some sense here to you here. So, some sort of conservative force is something that is path independent. Okay. So, for example, a good example of a conservative force would be gravitation. Okay, so let's say you're going to get an object and you're just going to lift this object up. And so it takes work to do that, right? It's got an entire planet pulling down on it. And so you got to supply a force and you're going to move it. So there's a net force up, there's a displacement up, and this force that you are working against, gravity, is a conservative force because how you move it from point A to point B does not matter. So let me kind of draw this out here. Let's say you've got this box here. Okay. And it's got some mass, and let's call this point A. And you're going to get it up here to point B. Okay, so your job is to get this box here, move it up to point B, and it takes you some work to do that. And so you could take this path right here, and this is the path that most people probably think about, and we'll call that path 1, right? So if you take path 1, how much work does it take? So I'll call this work. I'm going to put a little 1 here for path 1. And work is going to be your force here in the y direction times your displacement in the y direction, right? So remember, this is a dot product where the force and the displacement have got to be exactly in the same direction. And so the force that you've got to exert is at least the object's weight, right? If you don't supply enough newtons to overcome the object's weight, then gravity wins and it just sort of sits there, right? So if you have a refrigerator and this thing is 1,000 newtons and you can't lift it, well, okay, then it's just going to stay there. But you've got to supply at least the object's weight, and then it moves up a certain distance, right, directly upwards. And so this right here is what we're calling y. Okay, and so that's how much work it takes for you to go from point A to point B. And let's consider now another path. So let me get a let's get a different color. So let's say you do something like this, and we'll call that path number 2 right there. Okay, and so path number 2, you're starting at A and you're still ending up at B, but you're moving the box sideways here. Now, gravity works in one direction, right? It works straight down towards the center of the earth, and you're going up really against it. And so your work here in path 2 is the force that you're going to supply upwards times the displacement that you move it up. And the force that you've got to supply upwards is at least the object's weight, and you're going to lift it still exactly that same height. In other words, moving the box sideways, right, with some x displacement, when the force of gravity is downwards, those are at right angles to each other. When you do a dot product between x's and y's, right, you get the force times the displacement times the cosine of the angle between them, and the cosine of 90 is 0. So there is no work to move something sideways, right? There is no work to move an object in the x direction against gravity. So you can think of all sorts of different paths to go from point A to point B, and no matter how much sideways motion you entertain in that motion, there's no work against gravity this way. There's only work against gravity that way, right? Because gravity is a force this way, so it's really only the y component that's doing things. So it doesn't matter the path you take; it's going to take you the same amount of work to go from point A to point B, working against gravity. Right now, there might be other forces that you might have to consider. If you're really getting down to the brass tacks, maybe there's a bunch of air resistance, and maybe there's some friction in your joints, and the more sideways you move, right, there's more work that maybe you've got to do and so forth. But in working against gravity, it makes no difference which path you take. So this is why we say it's path independent. Now, a non-conservative force, there's a lot of non-conservative forces. The most obvious one would be probably something like friction, and it is very much path dependent. So let's take a look here and look at the idea of a non-conservative force. And these are path dependent. So how you go from point A to point B is going to be very important. So let's say you're looking down on a surface, right? It's just a floor or something like that. And you've got an object, and you go from point A and you're going to go to point B. And so this is some sort of surface, and on our planet, right, the surfaces have got some sort of friction, right? Even ice hockey rinks have got some friction and so forth. And so when you drag something from point A to point B, you can take path 1, okay? And in doing so, you are fighting some friction. in path A to point B. And so you go, well, okay, because in the back of your mind is this idea of work, and work against something like friction is the force of friction times the distance that friction acts over, right? So it's path dependent. It's the distance that friction acts over, and that would be this entire path right here, all the way from A to B, right? The floor is rough. And then if you choose a different path, say you do something like this, and you call that path 2, since that distance is longer, there is more work against friction, right? So if you're working against friction, the shortest distance is the best that you can really sort of do here. So different paths here will take different amounts of energy to go from point A to point B in working against something like friction. This is then called a non-conservative force. And so right now, when we start looking at this idea of conservation, there's really only a couple places that energy is going. And as you work your way through physics courses, you start learning more and more places that energy can be put. But right now, the situation is actually pretty straightforward, and there's only a couple accounts, right, where you can really kind of be depositing, any sort of amount of energy and that sort of thing. Okay, so we are going to revisit this idea of conservative and non-conservative forces, and we'll do it from a little bit more advanced standpoint. We'll look at a little bit of mathematics. It won't be, looking at vector fields or anything like that. But there is a nice way, if you have a conservative force, to be able to figure out exactly, how that affects the energy of an object and so forth. Okay, so types of energies. So, so far we have seen this idea of kinetic energy, and this is the energy of motion. So any object that is moving has this energy of motion, and even something like atoms and molecules, right? They're always kind of jiggling in some sort of material. And in something like a gas, they've got more freedom, and they're actually going pretty fast, maybe 500 meters per second. They have a lot of kinetic energy. And when you put them in like a liquid, they're not as free to move, but they still roll around. And so they've got a lot of kinetic energy. Then you get down to a solid, and they're in there and they're jiggling back and forth. So they still have this motion. So even atoms have got this kinetic energy here. And I'm going to typically use KE for that. And it's exactly what it was in chapter 7, 1/2 mv squared. And we have to be using kilograms here. And that velocity has to be in meters per second. And when we square that, that comes out in joules like always. Right? So that is really one type of energy that an object can have. If it's moving, it's got this type of kinetic energy. Now, probably more abstract is this idea of potential energies. This is energy that's really stored up, and it's stored maybe in a material, or it could be stored in a field, but you're storing energy somehow, some way, somewhere. Right? So this is some sort of stored energy. And it could be stored energy in a material, or in a field, or it could eventually be something like in a temperature, things like that. So there's a lot of places that we'll be able to store energy. Typically in physics 101 and 103, it's going to be stored in a material or in a field. And the field right now that we'll be dealing with is the gravity field. Eventually in physics 103, you'll be dealing with electric and magnetic fields, and you can store energy there as well. Physics 102, you can start storing energy in temperatures and things like this. Now, we've already worked out energy that gets stored in an elastic material, right? So like this is like springs and rubber bands and bows and arrows, any sort of bungee type material where it takes work to pull it apart, but you let go and now you can make something move, right? So work, and that work gets stored. So if you put in 100 joules of energy to stretch a bungee material, you can get 100 joules back in terms of making something move, in terms of its kinetic energy. So potential energies so far, That is the energy stored in an elastic material, and that was a 1/2 kx squared. And the work in some sort of elastic material, that 1/2 carries no units, but K is in newtons per meter, and X is in meters squared. And so what you're left with here is the meters canceling on the bottom, canceling one on the top. You have Newton times meters, and this is joules, like always. Okay, now the other place that we're going to store energy is in the gravity field. And so I just did an example where we're lifting something up against gravity. Okay, and so we're going to call this gravitational potential energy. And it's important to make the distinction here that G, the acceleration due to gravity, it's a constant if you're on the surface, right? It's 9.8 meters per second. But we've seen that the further you go up, away from the planet in like chapter 5 and chapter 6, when you're dealing with Newton's law of gravity, the force becomes less, which means the acceleration is less. And someplace up where like the space shuttle would be a couple hundred miles up, it's not 9.8, but it's not 0. It's like 9.2 meters per second. So as long as you stay, on the surface where most of us do all of our living, it's a constant. So this is gravitational potential energy, and I'm going to say, near the surface. And eventually, before chapter 8 is done, we're going to look at the idea of maybe getting a rocket and putting it out into space where it's a considerable distance away from planet Earth. And then the acceleration is not constant. And maybe if that rocket is coming towards Earth, the acceleration due to gravity is getting bigger and bigger, right? It's getting closer and closer to 9.8. And we'll see exactly how to deal with something like that. So, what we had here a moment ago, and it's really no different, that if you've got an object here, right? So let's say you've got this object and you're going to lift it up and you're going to put it into this new spot here. It takes work to do that, right? And so this thing is going to get displaced, right? Some vertical height against gravity. And so the work to go upwards is the force upwards dotted into the displacement upwards. And now the force upwards is the object's weight, and the displacement is just, some sort of height that you move the object in. And moving it sideways means nothing to gravity. This is how much work is taking place. This is how much work that a machine or you have to do to get that object to be up there. But the brilliant thing is that we have learned that energy that it took to put it there is now stored in that position in the gravity field. So if you actually let the object go, it starts moving, and eventually when it loses y meters of height, when it loses all that height, all that energy comes back in terms of motion, and it comes back in terms of kinetic energy at that precise moment. And so, gravitational potential energy near the surface, so PE, I'm going to put like a little G here for gravity because there's a potential energy for elastic materials, and there'll be other potential energies too, is exactly what we see here: mass times gravity times height. And this energy gets stored in the gravity field. The gravity field is a conservative force, and so your energy is sitting there somehow, some way. And if you take a look at the units here, this will come out in joules, just like any sort of energy should. So mass is going to be in kilograms, G is meters per second, and Y is in meters. And if you start taking a look at this, right, kilograms times meters per second, that's a Newton times a meter. And as long as there's a dot in between the two, that's a joule. So this will come out in joules. So energy gets stored up in these two places. Right now we can store it in a gravity field, or we can store it in an elastic material, and that's it. And then the other type of energy is energy of motion. So right now, there's really only three accounts that energy can be stored in. So one is the kinetic account. One is this account right here, elastic potential energy. And the third account is this right here, gravitational potential energy. Those are the only places right now that energy can go where it is safely stored or easily measured in terms of motion. Now, the other force that we have dealt with since chapter 5 is this friction force. And that's a force that we would call a dissipative force. It can take energy out of a system, but that does not mean that it's not something that we can't keep track of. So it might take energy out, and that's okay. That's not going to bother us really at all, because we have a good knowledge of using free body diagrams and how forces work over rough surfaces and things like that. We'll be able to deal with that situation. But, here is something very important, that definition. Here is something very important, storing energy. Anytime energy is involved, that essentially will be the fundamental level of understanding nature, really. Okay, so let us take a look at this idea of work by a non-conservative force, such as friction. And, I'm just going to use the definition here, that work is F dotted into some sort of displacement. Okay, now if you're working against friction, maybe I'll write it this way. I'll put a little FR for friction. And the force is the force of friction dotted into the displacement here. So sometimes your book will use an X, sometimes it'll use a Y if something's moving upwards, X moving sideways. Sometimes it just uses a generic D for displacement. But the force of friction is a coefficient, right? And if this is something that's moving, it's a kinetic coefficient times a normal force dotted into the displacement. And so here is something that can take energy out of a system, and that would be friction, right? So you can push a box and, it might move, 4 or 5 feet across the floor, and then it stops. You go, well, I gave it kinetic energy. Where'd it go? Well, friction ate up that energy. And maybe, and right now friction is just sort of this big ball that might contain a lot of stuff, right? Because the surfaces are rough, you might hear the box dragging, which that friction might create some sound waves. Maybe some energy is going that way. And because it's rough, maybe there's some thermal heat that's going to build up and so forth. But right now, we're just going to call all of that just the friction force. That's where some of that energy will happen to go. Now, the coefficient carries no units, but the normal force here carries newtons, right? And the displacement carries meters, so Newton times meters. This still will come out exactly in joules. So here is the work done by friction. And, we did some considerable work back in chapter 4 looking at level playing fields and objects dragging across it and trying to figure out that normal force, and then putting objects on hills. And so, those are the two places we got to be able to figure out normal forces. And we'll take a look at an example here, I think, in a little bit. Maybe, some box or something sliding down a hill and seeing exactly, how to figure out, how much energy is being, eaten up by friction and so forth. But this is another place that energy doesn't get stored, but it gets dissipated, right? So here's a dissipative force here. And so your world view right now is not very complicated. We've really now only got 4 places that energy can go. Motion, kinetic energy, stored up in an elastic material, stored up in the gravity field, or get eaten up by friction, and that's it, right? So these are the 4 places that energy can be going. So none of this is worthwhile, right? There's no reason to do all of these new definitions and these new concepts if there's something that's not underlying it, and there is something underlying all of this, and that's this idea of laws. Okay. Now your textbook will start using the law of thermodynamics, or the first law of thermodynamics, later on, but there's no reason why for us not to see this terminology right now. The first law of thermodynamics says something like this. In a closed system, we'll talk about what that means here in a moment, energy may change forms, but it is conserved. That's a law that you memorize. This is called the first law of thermodynamics. Right now in the textbook, it's going to be called the conservation of energy. Okay. But eventually, when you start looking at objects getting hot, getting cold, transferring that heat, how do you make an engine by exploding gasoline and making pistons move and turning flywheels, and eventually cars are going down the road and so forth. Then the idea of thermo, that is heat dynamics, shows up, but it's exactly the same law. In a closed system, energy may change forms, but it is conserved. In a closed system, this is a system where you're not adding energy, you're not taking energy out. Even if you have a dissipative force like friction, you still can see exactly where the energy might be going and so forth here. But we'll take a look at systems that may be conserved and systems that are not going to be conserved. Now, if there's something called the first law of thermodynamics, then there's going to be something called the second law. And the second law says if no energy is put into a system, the system will tend towards a lower energy state. And we find that to be true with all systems in nature that we've seen so far. And so, 100 years ago, if you're one of the pioneers and you're trying to study atoms and parts of atoms and what's inside of the nucleus, right? You can't see these things. The atom is, 10 to the minus 10 meters. The nucleus is 10 to the minus 15 meters, almost a million times smaller. And you can't see these things, but you find out that the parts in there are moving. They have certain properties, but one of the properties is that they have is that their energy content is conserved. And so, this works for boxes sliding down hills and roller coasters going over, big hills and little hills and so forth. But it makes no difference with the system. We find these two laws to be true. So we have the second law. And so, in Physics 101 terminology, the second law says if you put a ball on a hill, it rolls down the hill. It goes to a lower energy state. Okay, so it goes to a lower potential energy state, and that's what they do. In chapter 4 vocabulary, you would say, now the ball goes down the hill because there's a net force on it. Okay, so you can do your physics with objects moving in terms of forces, and that works. But now there's this other way of looking at how objects move. And so we have to start coming up with a whole bunch of new terminology. And this is the conservation laws. And eventually there will be 3. Conservation of energy is really the big one. In the next chapter, there'll be conservation of linear momentum, and then there eventually will be conservation of angular momentum. With those 3 conservation laws, you'll be able to talk about with precision an object's motion and how it's going to be moving in the future, make those predictions with the conservation laws, or you could do it with forces. Usually, the approach needs both. So it's usually complicated, and therefore you might have to use both approaches. So we learn both approaches here. Okay, so laws, memorize laws. Right? Know what these laws say, and I'm going to start putting these into practice to kind of show you what they mean in terms of trying to describe things in nature that might be moving, not moving, storing energy, taking energy out of the system, and so forth. So we'll look at all those situations here. Okay, so we've got some laws behind us. And so it's time to start putting these ideas into practice here. So here we've got, it says a 20 kilogram child slides down a slide. So, so you've got some sort of surface they're going to slide down. That's 5 meters. That is inclined at 22 degrees. How fast is the child going at the bottom of the slide? Okay. How fast is the child going down the slide when they have slid 1.25 meters down the incline? Well, there's no indication here that the slide has appreciable friction. So I'm going to assume here that, there is really sort of no friction here that I have to really kind of, worry about. So we can make a note of that. So we're going to ignore friction in this here. Okay, so we're going to ignore friction. And so the first thing that you've got to do is when you look at the situation here is start thinking in terms of where energy is and where it could be going and so forth. Okay, so you've got this incline here, and it says its length is 5 meters. So its length is 5 meters, and it's at 22 degrees. Okay, and the child, so the child, starts up here, and they're going to slide down here. Okay, and the first question is, how fast is the child going at the bottom of the slide? So we need to predict the speed here. Okay. Now, you can do this with chapter 4 and chapter 2 physics. That is, you can do a free body diagram. You can find the acceleration of the object coming down the slide. Then you can go to a kinematic. Okay, and that may be worthwhile to do, and we'll get an answer here. It takes a while to get that answer, but we'll get an answer here. Or we can use this idea that energy is somehow conserved here. And so, what I kind of do is take a look here and say, okay, right here, I'm going to call that point A. I'm going to call this down here point B. And at point A, when the child is just sitting there, does it have one of these 4 kinds of friction? It's not friction, but energy. Well, there's no friction here to deal with, so that one's out. There's no elastic materials here, so there's no rubber bands or bungee cords, so I'm not going to worry about that. But the child has a height and a gravity field. There is gravitational potential energy at point A, and that's the only energy they have. They're not moving here at all. So in your textbook, what he'll do, he'll write all 4 terms. He'll say at point A, friction, elastic materials, potential energy from gravity, and kinetic energy. And then he starts crossing them off, and that's fine, right? So he's just kind of showing you step for step what's going on. But I know that there's no friction because they're telling me to ignore it. There's no elastic materials, and they're not moving. So the only thing that's really sort of left is this gravitational potential energy. So I think that's the energy that this child has at point A. If there's no friction, they have that energy all the way down the slide until they hit the bottom of the slide. Okay, so they have potential energy at point A. Then I've got to ask myself, what kind of energy do they have at point B? At point B, there's no height left. Right? So Y is shrunk down to ground level, so there's no potential energy, but they're moving. And so it's a kinetic energy. And so it all goes into kinetic energy at point B. How do I know they're equal? Because I have a law up here that says in closed systems, energy can change forms, go from potential energy, gravitational potential energy. It can change forms into kinetic energy. It turns into motion, right? Things, when they go downhill, they go faster and faster and faster. And the child starts with that much potential energy at point A, and then they have this much kinetic energy at point B. So I'll write it that way. So it looks like maybe the energy that the child has is conserved as long as we're ignoring friction. But I'm trying to predict that speed here, and what I need is really the height here against gravity, right? Remember the discussion a little while ago on conservative forces, and gravity is a conservative force. It just cares about how you moved against gravity in the Y direction. It doesn't care about that the slide is going down kind of in an X direction here too. So you do have to figure out exactly, what that height happens to be. So maybe you have to use a sign here to do that, because the sine of 22 is the opposite side all over the hypotenuse. So I'm going to go to my calculator because I don't know what the sine of 22 is off the top of my head. Let's do that times 5 meters. And I think I'm getting on my calculator maybe like 1.87 meters or so. So 22 sine times 5. Yeah, I get the same thing here. Okay, so I'm just going to use 10 for gravity. 10 meters per second per second. Their height is 1.87 meters. And I have a 1/2 and I've got to solve for that velocity. And remember to take a square root when all is said and done here. So I've got 1.87 already in my calculator. I'm going to multiply it by 10, then multiply both sides by 2 to clear that fraction, and then take a square root. And I think I get the velocity at point B here to be something like maybe a 2.47 meters per second. And let me take a look at the problem. And everything looks like it's 3 sig fig, so I think I'll keep exactly that right there. Okay. Now, I think there is a part B here. It says, how fast is the child going when they have slid 1.25 meters down the incline? Okay, so we'll have to kind of worry about what that means here in a moment. So why don't you go ahead and think about that, and then we'll try to tackle that here very quickly. Part B, when they're only part way down the hill here. Okay, so maybe you've thought about how to sort of tackle part B here. How fast is the child going when they have slid 1.25 meters down the incline? I'm going to interpret that to mean that, they're like right here, where that distance is 1.25 meters. Okay, now you're going to have to ask yourself, out of these 4 places that energy could be, right? We have no friction in this problem. We have no elastic materials. So it's really just heights against the gravity field and energy of motion. Now, let's call this point C here. Point C, would the child be moving? Yes, they have kinetic energy. Inside of that term is really how fast they're going, right? There's a V inside of there, and that's what we're really trying to find. Now, do they have height at point C? And they do, right? It's not the height they started with, but can you do some geometry to find this height right here? I'll call that height of point C. Yeah, I think you can, right? You still have a right triangle, and so the hypotenuse is not 5 meters long, it's 1.25 meters less than that. But I think you can probably do some geometry and find that. But the physics is the important thing, is can you see where the energy is and where it's going? And so, I think if I were trying to do this part B here, my physics is going to look something like this. They've got potential energy at point A. Right. And that's all, right? They just start with the height and you let go of the child, and then they start moving because gravity starts pulling them down. So they start with some gravitational potential energy. Now, when they get to point C, you ask yourself, out of these 4 places, what kind of energy do they have? Throughout friction, throughout elastic materials? Are they moving? Yes. Okay, so they're moving. So the energy they started with went into motion at point C. And then the last category, do they have any height? Yes, they have potential energy at point C. And that is the physics, right? All we're doing here is accounting. It starts with some energy here, and then you can put it into these other categories. It can change forms from potential to kinetics to potentials. And those potentials could be elastic materials or the height against gravity. Or you could be losing some friction. In this case, we're not. But that's it, right? That is the physics. That is the accounting. That is using the first law of thermodynamics. I have a closed system. There's nobody who's doing work on the system. That would be the child is sliding down and then somebody pushes them faster, right? Now you've got an energy input in the system, and now the accounting is more complicated. Here we don't have that situation. They just start with potential energy at point A. When they hit point C, they still have height, so they still have some potential energy, but they're moving. And inside of that kinetic energy would be the speed that you're trying to pull out. So go ahead and try that. And if you can't get that that right, then ask about that in our discussion hours. But I think that right here is really the physics, right? That is using the law. The rest will just be some geometry to find these heights, and then the algebra and so forth. Okay, so some people find using conservation of energy, once they get used to it, to be simpler than using Newton's laws. There's no free body diagrams, at least so far. There's nothing here that's a vector, so directions aren't important. It's usually just accounting, right? You're being an accountant. You start with some money, and the money can go to a checking account. It can go to a money market. It can go to a savings account. And so you're just kind of moving monies around, and you're just trying to see, exactly where it's going. And so that takes, right, a little bit of thought. But right now, once again, right, you've only got the 4 accounts to be dealing with here. So let's take a look here at something else. Okay, here's something that looks like that we can do in chapter 2. A ball is thrown straight upward with a speed of 14 meters per second. How high will it go? How fast is it going when it's 3.40 meters above the launch point, heading upwards? Okay. So how high will it go? Well, my first instinct would be to use something like chapter 2 type stuff to answer, this first question. And, if I was going to do that, so let's call that actually like part A here. If I was going to use chapter 2 techniques, I would start looking at it like this, right? That we throw something up and I give it some sort of initial speed of 14 meters per second. And when it hits the top, right, when it hits the peak, its final speed is 0. And the question is, how high did it go? And I think there's a kinematic that will do that for us. So I think, and let me see here, maybe this one. So there's my kinematic, there's my physics. And I'll call all vectors going up positive, any vector coming down negative. And my final velocity, when I hit the peak, right, for a very brief time, it turns from my positive vectors into negative vectors, so it has to pass through 0. And I threw this thing up at 14 meters per second straight up. That's going to get squared. I'm going to use 10 for gravity. And it's a vector down, but that's one equation, that's one unknown. And so I'm going to get 14 on my calculator. I'm going to square that. And when I move it to the other side of the equal sign, it becomes negative, right? So I have negative 196, and that's meters squared, seconds squared. And then I divide that by negative 20, and that's meters per second squared equals delta y. And so when I take a look at my units, right, the second squares cancel nicely. This meters takes out 1, so I just have meters. So, I end up with something like, I'm getting like 9.8 here, maybe. I'm going to calculate it. Let's try that again. So, it looks like about 9.8 meters. Okay. So that's how high it goes. And that's how you would do that in chapter 2. And there's really nothing wrong with that approach here whatsoever. Now, let's take a look at this in terms of energy conservation. We're not dealing with any air friction here at all. So you're just dealing with the gravity field of Earth, and gravity is a nice conservative field. And so when you throw this object, right, I'm going to call that point A, and then it goes up and it hits point B. And you have to ask yourself, what kind of energy does it have at point A? Essentially, it's starting at ground level. And what you're going to do, you're going to give it kinetic energy, right? You're going to throw this thing upwards, and it goes up. When it hits point B at that very peak, it's got to stop and turn around, even though our eye doesn't quite see that. So at that point, it has no kinetic energy for a very brief time, but it does have this height, right? It has this potential energy up at point B. There's no elastic materials here. There is no working against friction. So there's, these 4 places that we have to kind of keep track of, but yeah, no friction, no elastic materials. And so it's just motion, that is speed going into a height against the gravity field. So I think that's going to be my physics here. My physics that is using this conservation idea is that the kinetic energy at point A all turns into potential energy at point B. What allows me to write that down? the first law of thermodynamics. Energy is conserved. It's changing forms. And I can look at the situation and say, well, I threw it. I gave it some motion. And eventually that motion all turns into height against the gravity field. And I think that really is the physics. And so there's how much kinetic energy it had at point A, and that all turns into a height at point B. And so we see once again that the object's mass doesn't really matter. And I threw this thing at 14 meters per second. That's going to get squared. Once again, I think I'll just use 10 for gravity. And I've got this y displacement. So I've got 14 squared, which is 196, and I divide both sides by 10, right? And this is going to come out to be exactly the same thing. Right, so it shouldn't matter how you do the physics, as long as we're using the laws correctly, we should get the same prediction of what's going to take place here, right? And that's always the power of the physical sciences, is that you can make these predictions here. So very good. So we know exactly how high this thing will go. And in one case, we use chapter 2, and now we're using chapter 8 type techniques to get exactly the same answer. Part B says, how fast is it going when it's 3.40 meters above the launch point heading upwards? Okay, so that's kind of up in here someplace. And so when I start looking at part B here, let's see if we've got enough room here. So let's call this point A. And now we're dealing with a point that is 3.4 meters. So let's call this point C. And this is 3.40 meters high. Now, at point C, once again, right, we throw friction out, we throw elastic materials out. At point C, is it moving? It is, right? Because we know it goes about 10 meters high. So this is only 3.4 meters high. So it's moving and it has height. And so here, what it's got is kinetic energy at point A, and that's all. But at point C, it's got kinetic, right? It's moving. So if it's moving, it's got kinetic energy. And it has some sort of height here, right? So I can see that it's 3.4 meters above the ground. So I kind of think that's my physics, that the energy at point A, right? So what you're really kind of doing is something like this. The energy at point A equals the energy at point, in this case, it's point C. And the energy at point A is this kinetic energy that I gave it at point A. Now, at point C, it is moving and it has some sort of height there, right? So the energy is in two accounts. So you throw it, and a little while later, it's still moving. So it still has motion upwards, but it also has now this new height against the gravity field. So it's slowing down because the gravity field is doing the work on it. And I think that is the physics. I've got to look at the situation and see, where did the energy start and what accounts is it going into? So the object's mass is in all terms. So I will just cancel that out. And now I'll just start sort of, working through the arithmetic here. So 1/2. And my velocity at point A was 14 meters per second, and that's going to get squared. And I've got a 1/2 here. And I'm trying to figure out that velocity at point C. And this last term, I've got gravity. And the height at this point here is 3.40 meters. Okay. And so this is the arithmetic that we've got to work out here. So I'm going to go to my calculator and get 14 and square that. I already know what that is. I'm going to cut it in half. Okay, so this right here is 98 on my calculator. And then 10 times 3.4 is 34. So minus 34. So 98 minus 34 is 64. Okay, so I'm running out of room here, but this is 64 equals 1/2 VC squared. So I'm going to multiply both sides by 2, and then I have to take a square root here. Okay, and when I do that, I get something like maybe like 11.3 meters per second. So hopefully I did everything on the calculator correctly there. But it started off at point A at 14 meters per second. So I'm expecting a number less than that. And I've got that, right? So I know it starts at 14. When it hits the peak, it's going 0. So it's something between 14 and 0. And, I get some sort of result. I mean, there's some, I'm having some confidence that, my calculator, is telling me the truth, that I'm not hitting the buttons wrong or something like that. So that's what's happening here, right? It starts off at kinetic energy because I threw the object, and at point C, it still has height and it still has motion. And so that's the 2 places that the energy is going. So I've got to look at the situation and always just carefully analyze it. And I've only really got these 4 options of where the energy really can be going. So that's what I'm always going to be looking at here. Okay, let's take a look here at another example. A 3-kilogram crate slides down a rough ramp. Okay, so it's rough. So now I think, we're going to have some friction involved here that we have to kind of deal with here. The ramp is 1 meter high and angled 30 degrees above the horizontal. The crate starts from rest and experiences a constant friction force of 5 newtons. Okay, predict the speed of the crate at the bottom of the ramp. Okay, this is almost like the first example of where the child is going down the slide, but we're adding the friction, right? We're adding the dissipative force here, but I'm not going to let that stop me. This is going to be something I still can do the accounting for. I'm still going to try to get a good idea of what's really kind of taking place here. So I've got some sort of ramp here, and we've got a box here. Okay, and it's 3 kilograms. Okay. And it slides down a rough ramp. The ramp is 1 meter high. Okay, so this right here is 1 meter high, and it's angled at 30 degrees. All right, so we've got this 30 degrees in here. Okay, and we have a constant friction force of 5 newtons. Okay, what we want to do is predict the speed here. Okay, so I think what I'm going to do is I'll just call this here point A. I'm going to call this here point B. Okay, and so what kind of energy does the object have at point A? It has gravitational potential energy. So, it says it starts from rest, so that's important, right? So nobody pushed it down the hill, then it would start with kinetic energy, but it doesn't. It just starts from rest. So you just put it there and you just kind of let this thing slide down the ramp. So I think at point A, it has gravitational potential energy. Right? It hasn't moved, so there's no friction to worry about yet. There's no elastic materials here. And so I think that's the only energy it can have. Now, at point B, I'm to assume that it's moving when it's the bottom of the hill here. So, if friction was so big, it could just hold the box there, but it sounds like, friction is not big enough to actually hold it there. And so we need to predict the speed at the bottom. And right at the bottom of the hill, right, the height as it goes down the hill, it gets smaller and smaller and smaller. And so at point B, there is no potential energy anymore, right? That has shrunk to 0, but it has motion. So it has kinetic energy. But the energy that you put in to put the box there doesn't all turn into kinetic at the bottom, because you have this roughness that you're fighting. You have something that's actually taking some energy out. And so that's like somebody's spending some money, right? So you start with $20, but then you spent $6 on something. And so something is taking money, taking energy out of the system, but it still allows me to account for what's rest, what's still there, what's left over. And so that's exactly what my physics is going to say, that I'm going to start with some potential energy at point A. and it's going to go into kinetic energy at point B. And that is the total physics if there is no friction, but there is friction. So the energy that I started with doesn't just go into motion. It also goes into working against friction, right? So you start with some dollars and friction is going to spend some for you, but the rest is going to go into motion at point B. Okay. And I think that's the physics. So I've got to be able to look at that situation and say, oh, it starts with a height against the gravity field. That's gravitational potential energy. At the bottom of the hill, it's moving. It has kinetic energy, but it has no more height. So there's no potential. There's no elastic materials. But I did have to work against friction as it slid down the hill. So this right here that I've got underlined, that is the physics. That is using the first law, right? You've got to be very clear with where does the energy start and what accounts do I see it going into. I see it going into motion, and I see it getting used up against friction. And there's really nothing more to do in terms of the accounting. Now the rest are mathematical details here. So my mathematical details may be easy, maybe they may not be easy. It just really depends on the situation. Okay, so that's how much energy it starts with, right? M times G times the height. That's so many joules. And that turns into a 1/2 mv at point B squared. So if there was no friction, I would have complete transformation of potential energy, gravitational potential energy, into this kinetic energy. But I'm working against friction, and work is the force of friction times or dotted into the displacement that friction is acting over, right? That's the definition of work. So work is F dot displacement. So I'm just using that definition, and I'm working against friction. So it's the friction force against the distance that friction acts over. Now, what is the distance that friction acts over? I kind of think friction is all along what I'm kind of highlighting here in yellow, right? That's the path that you're taking against friction from point A to point B. And I need to know exactly what that happens to be. So if you're really good at trigonometry, you might just look at that triangle and know exactly what it is. But if you don't, then you're going to have to really kind of, work that out here a little bit. But I think I need the hypotenuse length here in this triangle. So I think that's going to be a sine. The sine 30 is the opposite side all over the hypotenuse, which is the distance that friction acts over. So the distance that friction acts over is going to be 1 meter divided by the sine of 30, and the sine of 30 is 1/2. So I think the distance that friction acts over here is 2 meters. So I did not know at the beginning that I was going to be doing that, but the definitions are telling me that that's exactly a number that I'm going to sort of need here. Okay. Now it's a 3 kilogram crate. So we've got that number. 3 kilograms. I'll just use 10 for gravity. And it starts with a vertical height of 1 meter. Okay, so 3 times 10 is 30 times 1. So it starts with 30 joules of energy. And I've got a 1/2 here. Its mass is still 3 kilograms. I'm trying to find that velocity at the bottom of the hill. And the force of friction, they told me that up here, right? They tell me that the friction force is 5 newtons. And I'm lucky they told me that. Otherwise, I think I'd be doing a free body diagram here to figure out the force of friction, because the force of friction is the coefficient times the normal force. And I need to know the normal force. Somebody's already done that here for me. So that's nice. And I've got 2 meters here. So take a look, see here. This right here is 30 joules. And this right here is 10 joules. Okay, so I start with 30 joules of the object on top of the hill, but friction is going to take 10 out, right? I'm going to spend 10 joules on fighting friction. So the rest the other 20 joules goes into the kinetic energy pile, and there's only one speed that I can plop into 1/2 mv squared. That's going to give me 20 joules here. Okay, so some people will look at it exactly that way. I won't do any arithmetic here, but some people will look at, if I get this 30 joules and I subtract out the 10 joules that friction is eating up, that difference is what's going into the object's kinetic energy. And so this is just 20 joules here. So you've got 20 joules left to go into the object's motion. And there you go. Okay, so you've got some arithmetic to do here. I've got 20. I'm going to multiply both sides by 2 to clear that fraction. So I got 40 on one side, and then I'm going to divide both sides by 3. So 40 divided by 3 is 13 1/3, and I'm going to take a square root. And I get something like 3.65 on my calculator. So okay, so undoubtedly, if there was no friction, we would have a bigger kinetic energy. We'd have a bigger speed here. If we had a bigger friction force, right? If friction wasn't 5 newtons of force, if it was bigger, then eventually it would really reduce the kinetic energy. We get smaller speeds and things like that here. Even though we have a dissipative force right here, right? So this is energy that's getting eaten up because it's being subtracted here from when I started, but it still allows me to do the accounting. So that's not going to be something that's going to slow us down here at all. In fact, that's going to be something that's going to be very helpful in a lot of situations. And in fact, maybe I'll look at some examples that we did maybe back in like chapter 5 with friction, and we'll do them maybe the same way. And we'll do that that we did in chapter 5 with Newton's laws, free body diagrams, F equals ma. And then you can do it using these conservation ideas as well. And we should be getting the same answer no matter how we slice it. So hopefully this starts making some sense to you. And let's kind of keep going down. I think we still want to probably do something with some elastic materials here to see how that kind of plays into everything. And so here we've got a spring, and somebody's asking us a bunch of questions about the spring and what sort of motions it can give an object and so forth. So let's take a look at this and kind of see what's happening here. So take a moment, copy this down, and then try to eventually work this out on your own. After you kind of see me do it. But we have a spring, and it's got a constant of 300 newtons per meter. It has a 2 kilogram mass compressed against it. The spring is compressed 40 centimeters, and the mass in the spring are released. So it's a horizontal spring, right? So maybe it's attached to a wall, and you've got a spring here, and you get a 2 kilogram object, and you compress the spring, and then you let go, and then that compression is going to turn into motion here. Okay, so horizontal spring. It's got a fairly decent amount of stiffness here. The K is 300. So you got a mass compressed against it, and you compress it 40 centimeters, and the mass and the spring are released. Okay, so how much energy is stored in the spring? Okay, so that will be probably the easy part here. So the energy stored in some sort of elastic material is that right there. That's how much work it takes to compress it. But because it's a conservative system, that's how much energy is actually stored in it, right? And so what you're thinking here is that the energy to compress the spring is the same as, equal to the energy stored in the spring while compressed. So that's how you're thinking about this, right? It's a nice conservative system. So like gravity, the energy it takes to put an object up high, that work that you did, all of those joules now are exactly what's stored in that position. So if it takes you 25 joules to put a box up on a shelf, then that object has 25 joules of potential energy stored. If it takes you so many joules to compress a spring, then exactly that number of joules is stored in that elastic material. That's what it means that we have these conservative systems here. So I'm going to compress the spring. It takes me some work to do that, but all that energy is now stored, because if I let go, all that energy can come back to me in different forms and so forth. So that is the beauty of these conservation laws, is that all we're doing is looking at numbers. What did I put into the system? And if it's a nice conserved system, then I'm going to have that energy stored up here. So my energy here that's stored up in an elastic material is 1/2 K, in this case is 300. And so it looks like it was really measured pretty well, times how far you compressed it. Okay. And so I compressed this 0.40 meters, and that's what's going to get squared. Okay, 1/2 kx squared. So k is the spring constant. X from chapter 7 is really the compression that we've got here on the spring. So springs typically don't store a lot of energy, but I'm going to go to my calculator and sort of do a 0.4, and I'm going to square that. Times 300 times 1/2, and I get 24 joules. So 0.4 times 0.4 times 150, and I get 24 joules here. Okay. I don't have right now a great feeling of if that's a lot of energy or not. But typically, springs don't store a lot of energy. This is actually a small amount of energy. So I think we'll start getting a better feel of what joules actually means here. And so I'll be looking at that situation here. So maybe we can get some sort of idea of exactly what's taking place here. Okay. So I think that's probably the easy part here. Part B, how fast will the mass be traveling just as it loses contact with the spring? Okay, so in something like this here, right, you've got this spring here, and you've squished it up, and you've got this object here. And eventually, when you release it, right, the spring now is back to its natural length. And so this object is going to start moving. Okay, so you store 24 joules into the elastic material. And when the elastic material regains its natural form, it goes back to its natural length, there's no more X, there's no more compression or extension in the spring. And so all the energy is out of the spring, right? So here you've got energy stored in the material. And that's because it is compressed. So when it's no longer compressed, down here, you have to ask yourself, where did the energy go? Well, there's no talk about friction, so we throw that out. There's no height here, right? It says it's horizontal, so there's nothing here to really worry about in terms of it going up against gravity or anything like that. So there's no energy going into gravitational potential energy, but it makes this object start moving. And so, this is a nice behaving spring. All the energy that I stored in it, all will go into the object's motion here, right? And so I've got kinetic energy here. And that kinetic energy has got to be worth 24 joules once the spring has lost all of its energy that was stored in it. And I kind of think that's, really the thinking that I'm going to have here. So let me go back and take a look. It says, how fast will the mass be traveling just as it loses contact with the spring? So when you lose contact with the spring, that means the spring has lost all of its compression. So all the energy now is gone, right? And so I think my physics here is going to be something like this, that the energy stored in the spring all turns into kinetic energy at the moment when there is no compression in the spring. So once the spring has lost all of its energy, then it all goes into motion here. And so this is 24 joules. That was what's stored. And it can all go into this object's motion. It will all go into kinetic energy here. So we have to know what that object's mass is. And so undoubtedly it was told us it's 2 kilograms. Okay. And so I've got this 24 joules here. There's a 1/2. This thing is 2 kilograms. So there's only one velocity that the object can really have to give it 24 joules of kinetic energy, and that's going to be the square root of 24. So it's almost 5. 24 square root, 4.8, about 4.90, I think, something like that. So that's the velocity that the object has to have for it to have 24 joules of energy. If it doesn't have 24 joules of energy, then the obvious question is, well, where'd the energy go, right? It went someplace and we can track it down. Now, it may go into forms that you and I can't really readily use, but we still can track that down. Okay, so I think that's how I'm going to think about, doing something like, some sort of elastic material here. There's a part B. How high will the mass travel up a frictionless ramp? Okay, so it sounds like to me here that what we've got in part C is you've got this compressed spring, and it's horizontal, and then there is, some sort of ramp over here. And eventually, since there's no friction being involved, it's going to end up right at some spot here, and I'll call that spot B. And so you have to ask yourself, they're asking for how high will it go up a ramp. Okay, so when it goes up the ramp, eventually it goes and it stops. And so when it stops here, that implies, right, that the kinetic energy goes to 0. There is no friction. It's not pushing against an elastic material. And so at point B, the only energy that I see that it has is this height against the gravity field. Okay, so I think that's going to be my physics here. I'm going to say something like this. I'm going to say that the energy stored in the spring can all turn into potential energy at point B. And the energy that was stored in the spring was 24 joules. And my potential energy is mass times gravity times the height at that point. And that's what you're trying to figure out, right? You're trying to figure out exactly what that little height right there happens to be. How high can this thing go up a ramp here? So now, if I can get that situation analyzed and see where the energy starts, it's stored in a spring, and I know that number. And now the thing is going to go up a hill, and it's a smooth hill. There's no friction, so it's just a matter of 24 joules turning into 24 joules of height. 24 joules stored in the spring turns into 24 joules in height, and there's only one height that will actually give me 24 joules. So how do I figure energy with heights? Mass times gravity times that height here. And so I think that's going to be the arithmetic that we have to do here. And so this object has 2 kilograms of mass. I'll just use 10 for gravity. And there's my height right there. So I'm going to have 24 on my calculator. I need to divide both sides by 2 times 10 divided by 20. And I get 1.2 meters. Okay, very cool. Some of you that are coming out of Physics 165 might be looking at it and saying, hey, easy peasy. That's exactly the way that I think it should be working, and it does work very simple like that. There will be situations where it'll get more complicated, and we'll take a look, right? We'll start making life a little more detailed here as we go on. So, okay, so we've taken a look at heights turning into kinetic energies. Right, a child coming down a slide. We looked at somebody throwing something up. When you throw it, you give it kinetic energy, and that kinetic energy turning into potential energies. And we've looked at something that's starting up high and having a rough dissipative friction force, taking some energy out. And now we've got some energy stored in a spring, it turning into motion, kinetic energy, and then eventually turning into a gravitational potential energy. Okay. So we've looked at, a lot of the situations here. There's only 4 places, right? The energy could be going. And so we've almost looked at, most of the different types of situations that you can kind of run into here. So, so hopefully this is making sense, and you're kind of seeing how the accounting is taking place here. So you always have to analyze the situation and figure out where the energy is starting and where it's going. Okay, so let me scroll down here a little bit. And let's start taking a look at these units here and see if we can't get a better feel of this thing called a joule, and whether that's a lot or anything like that here or not. So the units of energy. Energy is the ability to do work. Work means that you can push something and make it move. Right? And so it's a Newton dotted into a meter, right? Where that's the dot product. And what is the dot product? It is a vector times a vector in the same direction, right? These are exactly the same direction. That's what the dot product implies, that you get the components of each one and multiply them that are in the same direction. And that turns out to be a joule, which is abbreviated J, okay? Now, in America, we typically start doing things with energy still in calories and so forth here. Okay, and so it's probably worthwhile to talk about this conversion between joules and calories. And I think the sheet here, you've got this probably in your package of stuff that's on Canvas. So eventually at the bottom of that page, you're going to see a lady doing some lifts here with a little weight and so forth, and we'll take a look at that. So I think you've got this sheet here that you can kind of dig out and kind of start filling in as we go along. So the conversion to calories, and kind of notice how I've got this written down, right? There's calories here with the little c, and then there's calories with the big C, and they are not the same thing. And so calories with a little c would kind of be like the science calories. That's how, just until a few years ago, how all my colleagues in chemistry would still be doing their energies and so forth. Calories with a capital C are food calories, and that's what you see written on the back of a package of like a candy bar or potato chips or a soda or something like that. So now the conversion, I've got the the book sitting right here, and so if I just kind of take a look at the inside cover, we've got a lot of conversions there, and I sort of see the conversion right underneath where it says energy and work, and so he uses 4.19, and so that's probably a good enough number for us here, and so what I sort of see there is 1 kcal. Okay, so it looks like that we've got 1 cal is 4.19 joules. Okay, now these food calories with a capital C, 1 cal happens to be 1,000 little food calories. Okay, so when you read your soda, and like if it's not a diet soda, it'll be close to like 150 calories, something like that, but it'll be capital C, right? So that's really 150,000 little C's here. And so I think that's the number that I'm going to use here. So this is an advertisement I took out of a magazine. I don't know who the Atom Corporation is, but this is something they had in a magazine. It says, lifting weights is an effective way to burn calories and lose weight. Okay, so we have a lady, she drank a soda, 150 calories, and now she feels guilty. And she says, okay, I'm going to work this off, right? I'm going to get a weight, and I'm going to start moving a little bit of weight against gravity and start working this off here. Okay, so let's say, for example, that she actually wants to work off the soda that she drank. So the soda has something like 150. I've seen some sodas that are a little less, and I've seen some that are a little more, but this is a pretty good number. So how many times does she have to lift this weight? And obviously the advertisement does not tell me the size of the weight or anything like that, but I think we can do something called a Fermi calculation, that is, just make some reasonable approximations and so forth. So how much weight do you put in your hand when you're doing these types of things here? And I think typically they're probably either like 5-pound weights, or they're maybe 10-pound weights here. And let's just say that I'm looking at the picture here, that's maybe like a 5-pound weight. And so 5 pounds divided by 2.2, it's not a great number here, but this is about 2.5 kilograms or something like that. So let's say that this is 2.5 kilograms. And how high do you lift it against gravity when you do this? And I'm just trying to get a nice round figure. It's probably not as high as this, but maybe like a 0.5 meter or something like that. And so it's probably something pretty close to that, 0.5 meter. Okay, so I'm just making a reasonable guess of what that weight looks like. It's either 5 or 10 pounds, so I'm just calling it a 5-pounder. So it's pretty close to 2.5 kilograms, and she probably lifts it about a 0.5 meter. Okay, so let's go back here. And she's trying to work off 150 calories. This is 150 capital calories. And so that is 150,000 little calories. Okay, so that capital really implies like kilocalories or so. And then I'm just using the conversion in your book, and 1 little calorie is about 4.19 joules here. Okay, so I'm just going to change those units here. So let me go and get 150,000 multiplied by 4.19. And I get something about I'll just kind of round this off here a little bit, about 630,000 joules here. Okay, does that give me an idea of what a joule happens to be? So a soda, a regular soda that's not diet, has something like a little bit more than 500,000 joules. So joules are a pretty small unit, right? So one soda has more than 500,000 joules in there. And so that sounds like a big number. So eventually the numbers will get so big that we'll have to start cutting them down, because people don't want to talk about hundreds of thousands or millions of joules. So we'll start cutting those down to get reasonable numbers. And that's just something that people do all the time. Okay, so this is how much energy she has to try to work off here. And how's she going to do that? She's going to lift this object up. So she's going to increase the potential energy of this object, right? So the potential energy increase is the object's mass times gravity times the height that she lifted. And so I'm going to guess that this is close to 2.5 kilograms. I'll just use 10 for gravity. And we're going to lift it about 0.5 meter worth. So when you lift it once, you're increasing its potential energy. That's how much work you did at a minimum, right? You probably still have some friction in your joints and things like that. But this is about 12.5 joules to lift once. Okay. So that's how much energy she expends to lift at one time. And she has to work off 630,000 joules at 12.5 joules a pop. So let me see, 630,000 divided by 12.5, and I get about 50,000 repetitions. Yeah, let's just call it reps. Making 50,000 reps. Okay, so she's certainly not going to do 50,000 reps. I think, people usually do 10 or 20 of these, and then kind of go to the other arm, do 10 or 20, and then maybe come back to that arm, do 10 or 20, and go back to the other arm, and that might be it. Or they might do that, 3 or 4 times. So, I think on a good workout, you might be doing like 100 of these things. There's probably a moral to the story here, and what would be the moral of the story? Some people might say, well, don't drink soda. And, I'm kind of thinking, exercise, sort of why bother? Because you're not going to work off those calories. Now, this happens to be, some of you will know, a pretty poor way of trying to burn calories, right? If you're really trying to lift this weight, you're probably sort of trying to tone the muscles and so forth. Probably the better thing to do is lift your entire body, which means go up a hill. And so, a lot of times coaches and so forth will have people like run up hills in a stadium and things like that, because now you're lifting your entire body, and that's a lot more mass than something like this, and it's a lot more height. And now you really can be working off, those types of calories. So you need probably more like an aerobic exercise here to do this, as opposed to just like lifting weights and so forth. So lifting weights, it burns some stuff, but not a lot. Now, your body is going to use some of those calories just to live, right? You've got kinetic energy of the lungs, right? They're moving and they're pulling in air and they're exhaling air. Your heart is moving, right? There's kinetic energy there. It's moving fluids throughout your body. Your brain is moving electrons up and down your body, electrical signals. So your body needs energy just to live. So some of those 150 food calories will get eaten up by your body just to stay alive and to maintain the temperature and so forth. But very difficult to work it off some way like this. But I think it's kind of instructive to see that, a calorie is something like 500,000 joules, right? Really a little bit more than that. So it gives me an idea that a joule is actually a very, very small number here. Okay. So this is a little bit of idea of that, and this is probably a good place to maybe be wrapping this up. Eventually, we'll be going here to Chapter 8, Part 2, and so I think this is a good place to stop, and then we'll do another lesson here and looking at some more of the details that start showing up in Chapter 8. So I hope this helps you start seeing exactly how to use the first law of thermodynamics in some situations, and we'll keep looking at maybe some more complex situations here, and I'm seeing exactly how to deal with these conservative and non-conservative forces here more in terms of a mathematical operation here. So I'll see you soon, and hopefully this helps you out here.